is, but if you pick the resonance energies, you can map out where is the uranium, you see our tungsten cloud again, and then you see the xenon, you see the gadolinium of course, and you see the cobalt-59 that's always in steel. So we can make element maps and show distributions of isotopes or elements in our field of view. And then we said, well, we know the volume of where the xenon gas is. We know how many nuclei of xenon we have. And then we started to measure the pressure with the resonances. So with the resonance method, with the neutrons, we get about 740 pascals. The gauge on that steel said something like 760 pascals. So now we have a method to measure the partial pressure. Even this works for gas mixes. Or for the nuclear fuel people, we can measure the fission gas non-destructively while it's still in a container. Or if you have an inner and outer container, we did some leak testing, right? When the inner container pops, the gas gets released, and we see it in a volume non-destructively. So why do this at LANSCE? Well, first of all, as I hopefully convinced you, takeaway message here is you need the pulsed neutrons. You have these neutrons also in a reactor, but they're in the 10 to the minus 4 flux, and you don't have a convenient way to get them out of your reactor spectrum. Making your neutrons in pulses is very beneficial for this. You need a fairly narrow pulse width, so at LANSCE we have 270 nanoseconds pulse to pulse, base to base. At the SNS, they have 700 nanoseconds. That's still okay. You want to put this into relation to how long does it take to moderate your neutrons. If that time, you want to be shorter than your moderation time. But for instance, at the European spallation source, this is 3 milliseconds, not micro. This is 3 millisecond long pulses. So for these purposes, the ESS is not even a pulsed source. It's some semi-continuous source. And you cannot do this method efficiently there. You also want to have single pulses. At JPark for sometimes they had double pulses, and then especially for nuclear energy research, you need to be able at your facility to handle these materials. If you go to SNS or in JPark, for instance, they have a beautiful beamline, but you cannot even get depleted uranium through the door. So LANSCE is unique in that sense, right? That we can bring our authorization basis allows us to have 340 plutonium equivalent grams on site. Right? That's a lot of plutonium, and if you convert that to fissionable uranium, it's even more. So we can handle these type of fuels. We have the infrastructure for irradiated materials, so in that sense, LANSCE is unique. With that, let's move to the diffraction part. Are we on time? No, it's okay. So now we move to HIPPO, the high pressure preferred orientation diffractometer. You can make a nice icon cartoon of it, much better than you want to keep that in mind if you name your beamline. So now we deal with diffraction. So diffraction is sensitive to the arrangement of the atoms. So this is both carbon. Once carbon's atoms arranged in the crystal structure of graphite, right? You have the layers, and once carbon atoms arranged in the crystal structure of diamond. We all know those are very, very different mechanical properties, but it all goes back to the crystal structure. So with powder diffraction, we look a lot at structure-property relationships. How do these people deform? How do these materials deform? What happens during phase transformations? If you put these materials in HIPPO, for graphite you get this diffraction pattern. For diamond, you get this diffraction pattern. So this is the lattice spacing, right? The distance of the atomic layers, and then here's the intensity. So whenever the neutron wavelengths is compatible from Bragg's law, as I show on the next slide, with one of the spacings, you get a reflection, and you can measure from that what materials do you have in the beam. So that's slide 1 of the fundamentals. So first of all, how does diffraction work? We now use that neutrons are such small particles that they both have quantum mechanical properties. You can assign with de Broglie's relationship of wavelengths, h bar k, or h over 2 pi times 2 pi over lambda, or you cancel the 2 pi's, you get h over lambda. And then you have the classical mechanics momentum, mass times velocity, or again, the flight path length and the time. You equate the two, right? The quantum mechanical momentum is the same as the classical mechanics, and then you can deduce this equation down here that I fancily highlighted. Wavelengths is equal Planck's constants times the time of flight divided by mass of the neutrons divided by L. Now, instead of assigning an energy, I can convert the time of flight to a wavelength. And then we're probably all familiar with Bragg's law. I see a reflection if and only if the wavelengths equals 2 times the d spacing of the lattice spacing that reflects times sine theta. That wavelength has to be the same as the ht over ml that I just derived. So now I can solve this for d, and then I get a bunch of constants. Planck's constant, number 2 is a constant, mass of the neutron doesn't change, flight path length doesn't change, we don't move the detector, so all of this is constant, and my only parameter is the time of flight. So when I measure diffracted intensity as a function of time of flight, I have a linear conversion to d spacing, and then I can analyze these crystal structures, right? And then the yellow lattice plane is a slightly narrower distance or slightly shorter distance from atom plane to atom plane, so it shows up at a lower d spacing than the red one here, which is at a higher d spacing. So that's in a nutshell how diffraction works. So now we need a completely different setup, and this is Hippo here. So the beam, the pulses come from this direction here, enter this blue sample tank, and then all the red areas are neutron detectors. So with Hippo, I cover about 25% of the sphere around the sample with detectors. That means I capture a lot of them, and I can either measure fairly quickly, or I probe a lot of sample directions for texture measurements. Then we have a sample changer robot, a robotic arm basically, that can pick up samples and run them through. We can measure a piece of steel we can characterize in 5 minutes. If it's not a multi-phase steel and I look for 2% ferrite or something like that, so we need these sample changer robots. It's too short of beam times to manually change samples all the time. But I can also use this robot to scan samples, to move samples in the beam. So we use that for the nuclear fuels. We build a cadmium slit. Cadmium absorbs the thermal neutrons, right? And then and the red here is my 10 millimeter beam spot. I only probe a 2 millimeter slice of my sample. And then we had a fuel pellet behind that cadmium and scanned it through. So now I can do diffraction characterization of cylindrical samples, in particular nuclear fuels. Example shown here. So here's the CT slice of a fuel, and here's the areal density I get from the transmission, right, what I discussed before. And now I can also get this diffraction data. So I see diffraction peaks. This is a composite fuel, so I see diffraction peaks of the hexagonal uranium-3 silicon-5 silicide fuel, the cubic uranium nitride, and I see the steel container. They all diffract. I can characterize them all. Then I get parameters like the volume fraction of each phase, right? So in green here is the U3SI5, in blue is the steel, and the nitride is shown in the red dot, so I don't see much variation in the volume fractions. That means that all these pellets have the same volume fraction of the phases. But if I then look at the unit cell dimensions of the U3SI5, I see that the data points that correspond to the first pellet are significantly smaller than the data points of the other pellets. So there is something different. I can then also measure the, we see here also a little bit more scatter in the areal density for this first one. I can then measure the orientation distribution of the crystallites that make up this polycrystalline fuel pellet. If you have the nitride here has what's called a random orientation, meaning all the possible orientations have the same probability. The silicide, on the other hand, the 002, those are the c-axes, right? So I see 2 maxima in the c-axis, and then the a-axis is under 90 degrees in this hexagonal crystal structure. I see 3 spots here that correspond to this c-axis, and then the second one, there are 2 weaker maxima here. So that means that in this slice, the silicide phase only has 2 crystal orientations. It's almost like a single crystal. Well, it's 2 single crystals. And what we think has happened here is that during the annealing, that nominally should be just below the melting point of the silicide phase, this sample, as we found out later, was at the front of the tray, so the circulating atmosphere, helium atmosphere or argon or whatever they had in that furnace, heated that first sample a lot more. Why is that important? If you put this in the research reactor and you heat it, the C and A axes expand at different rates. So you destroy the sample simply by the mechanical stresses. You don't even need irradiation, right? This sample didn't stick out from the mass, didn't stick out from the visual inspection. This would have gone undetected, right? So the neutrons having these multi-scale characterizations, we can give you extra parameters. So what happened here is that this material, the silicide melted and then re-solidified. The blue phase here, that's where the silicide is. It re-solidified as two single crystals, which is completely different from what you think you put in there, has different properties and everything. So one of our value propositions to industry or NE researchers that we can characterize on a very detailed level the materials that go in the test reactor. Microstructure, phase composition, texture, strains, all these kind of things. Now in the last part, a few words on laser-based pulse neutron sources. If you want to ultimately characterize also a fuel that was in the test reactor, right, it comes out, it's very radioactive. Right now we have to ship it to LANSCE, we're working on that. We have to characterize it and ship it back. If you lease one of those type B shipping containers, or type A, one of the nasty ones, the bigger ones, it's $200,000 lease fee plus a trucker. So it's $250,000 on the way down to Los Alamos and $250,000 on the way back to Idaho National Lab, because I don't want to keep that fuel forever. So we were talking something on the order of $500,000 just shipment cost. So part of our research for the nuclear energy program is to look into sources. How can we bring this capability to Idaho National Lab, that they pull something out of the test reactor, they characterize it, they continue irradiation, or they know, okay, we need to cut it open here because there's something really interesting at 2.7 millimeters into that second pellet. So one of the ideas is laser-based pulse neutron sources. So let's look into, so right now, I hopefully convince you that pulse neutrons are much better than a little trigger reactor or some reactor-based neutrons. You get a lot more bang for your buck. Right now, in order to make these, you need some sort of a linear accelerator. To rebuild this, it's on the order of $1 billion. It's a large footprint, right, 800 meters long. You need air conditioning, you need electrical power for the accelerator. So when we run, back in the old days, 50% of the electricity that went into Los Alamos County went into this accelerator. Now we have supercomputers and other wastes of energy. But still the electricity bill is about $1 million a month. On top of that, you have to staff a lot of people. The central control room alone is on the order of 6 people day shift, 6 people night shift. So the operational cost of an accelerator like this is pretty high. Our target is shown here. So the protons come from the top, they hit this tungsten piece, right? A stack of tungsten disks where the spallation happens. So the 20 centimeters that this stack is high, that's driven by the slowdown of the protons, the stopping lengths of protons in tungsten. And then this whole thing lights up. Neutrons go everywhere. Our moderators are down here, right? So if this thing, the blue thing, lights up everywhere, you can imagine that only a small fraction makes it through a moderator surface, and then it's only a finite probability, it's not certain, that this neutron gets moderated. So from all the neutrons that this target produces, a lot of them are lost bouncing around here in the lead and getting lost, and only a small fraction makes it into the moderator, and then the beamlines are perpendicular to that moderator. So that's how we do it right now. For the lasers, if you have a very intense, short laser pulse that hits a thin foil, and thin meaning something like 100 nanometer, of deuterated plastic, what happens then is that the photons drive out the electron, or a fraction of the electrons, let's say half, and then for a short moment, you have a lot of electrons at a few micrometers away from this target. And you're left with something in here that your bonds don't have any meaning anymore because a lot of the electrons are gone. And that means that you have a very strong field, like teravolts or so, from the electrons on the then positively charged remaining atoms that used to be your thin film. So what happens is then that the cations get accelerated, and because the electrons are outside the sheet, they get all accelerated in one direction pretty much. And if you have then a target here, for instance beryllium, remember that this was deuterated plastic, so now the accelerated deuterium nuclei hit the beryllium target, and then what happens, one of the reactions that can happen is deuteron breakup. So you have this proton-neutron dumbbell flying around, and in 50% of the cases, when it breaks, a neutron keeps traveling, and in 50% of the cases, a proton keeps traveling. If the neutron keeps traveling and there's no problem getting out of this beryllium chunk, it's like 2 centimeters or so of beryllium, it just goes forward. If the proton travels, it gets stopped and makes hard X-rays. But in, let's say, 50% of the cases, the neutrons travel forward, so now I have a forward traveling neutron beam in a very short pulse, right? So the laser's pulse is some 150 femtoseconds long or something like that. With all the other stuff going on, you still have a sub-nanosecond short neutron pulse. LANSCE is 270 nanoseconds. This is sub-nanosecond, so very short pulses. Question?
How do you get the directionality of the neutron pulse?
Because it's a kinetic. It's a what do you call it? It's a breakup, right? There's momentum conservation. It's not a nuclear reaction.
Oh.
Spallation, fission, those are nuclear reactions, and you lose the directionality of the incoming neutron. Here, think of it of a dumbbell that flies, and one of the weights of the dumbbell gets stopped, the other one keeps going.
I see.
So the momentum conservation applies in this reaction. It's not a nuclear reaction. Right, so now you have a forward traveling intense neutron beam, and we replace this half-mile long accelerator with a few micrometers for the field, and this large $10 million target with somewhat inefficient target to moderator coupling with a little piece of beryllium. So I think that's what, yeah, so from the accelerator shrinks from half a mile to half a micron, and the target moderator shrinks from about, this thing is 3 meters high, to some 3 centimeters of beryllium. And the cost shrinks from something like $1 billion to something on the order of 10 million, some 40, 50, 60 million dollars for the first few, with the idea being that in the future that gets even cheaper. So that's the idea of laser-driven neutron sources. Why is it interesting now? If you look here as a function of year of time, basically the energy or the power of lasers, they are on this exponential growth, right? The neutron sources, on the other hand, are pretty flat, right? They sell a factor of 10 as the best and biggest neutron source, like the ESS, but it's a political statement. You make more neutrons, but they're in a pulse structure that doesn't allow you to use a lot of them, and a lot of them are lost in the shielding because they never see a moderator. However, with the lasers, if you can convert this to neutron flux and it continues to increase, we might get, as a neutron community, might get out of this flat increase, flat growth. In Los Alamos, I claim we are in a good position to develop this because some of the physics, what happens when a lot of photons interact with some material, that is new physics, right? And Cameron and others are studying this, but it's a fairly new field. The first shot on these kind of things was 1998, right? At Livermore, somewhere around there. So the field is not even 20 years old. So there's a lot of interesting stuff still to be discovered. One of the particle interaction codes at Los Alamos, they predicted what they called the breakout afterburner effect. If you have these electrons go out and then you have the other electrons that are still in your thin film, because you have that coherent light, they start oscillating all at the same frequency, then become relativistically heavy, and then there's no difference anymore between the electrons that have become relativistically heavy and the cations. And then you can couple the laser, if it's properly shaped, with whatever is left of your target at that moment, and you get a boost in energy. So they predicted that in the middle of the laser pulse, the acceleration energy of the particles increases by a factor of 5 or 6. And that increases the number of neutrons you get out of them, because the cross sections are better than linear. So that was theoretically predicted in the 2007 simulations on what was then one of the fastest computers in the world, the Roadrunner in Los Alamos. And then experimentally proven at the Trident laser at Los Alamos in, 2012, somewhere around there. So this works, and this is one example of the new physics that nobody conventionally thinks about, right? I mean, who thinks about a ton of photons interacting with materials? That just as an illustration, it's a new field, and we're already there that we can do useful stuff. So here are some of those targets. So that was tried. You burn a hole, you blast it all out, right? So deuterated targets or protonated targets. You can do carbon. The beauty of this neutron pulse traveling forward is that now it's very easy to capture it in a moderator. I showed you with our spallation target, we lose 2 orders of magnitude because this big chunk of tungsten lights up, neutrons go everywhere, and my moderators are down here. So only a small fraction hits the moderator. With the lasers, I just put a piece of plastic around that piece of beryllium. I capture 100% of my produced neutrons. So I'm a factor of 2 orders of magnitude more efficient right off the bat because these neutrons are traveling forward. That has been measured, right? So here is a stereographic plot, how many neutrons you get as a function of direction. So you get very few in backscattering and to the left and right, but predominantly coming forward. Here is number of neutrons as a function of target thickness, and as that Bohr physics and the regular mass describes, there's a sweet spot for the target thickness. So again, you have to understand that. If your laser pulse and your target thickness don't agree, you produce orders of magnitude less neutrons as if they both match. But somebody has to understand that. So this is what's going on right now. These are single-shot data from Trident, which was, in the infinite wisdom of the institution I work for, also shut down. And here is a number of neutrons, or transmission basically. You see a small dip here, but that dip happens to be right at an indium resonance. So with a single shot of the laser Trident, we believe we can see a resonance, right? That for a single shot at LANSCE, that's about, you would get somewhat better statistics, but you need normally more pulses. This is a thermalized spectrum, so we try to do diffraction. We see a Maxwellian spectrum as you would expect it after we moderate it. So we're getting to the point that we can produce useful data, and for instance at Bella, we're looking forward to seeing these laser sources operating at 1 Hertz, 10 Hertz or something like that, because Trident had old optics, and if you blast that much energy through a lens, it warps, right? The thermal expansion defocuses your lens enough that you have to wait 90 minutes for it to cool down, and even if it goes from room temperature to 40 degrees C, it doesn't work that well. We brought our imaging detectors, so here is a single shot pulse. So up here, if you do some image processing, you can see Trident and neutrons for sale as an attempt, a desperate attempt to increase funding, but it still shut us down. But what we learned here with these images is that for imaging, the small source size of these lasers is brilliant. It's great. Why is that? If you have a small source size, you have a divergent beam. You have built-in magnification. If you have an X-ray source that does it by Bremsstrahlung, you need about 1 millimeter or more to slow down your electrons, and your source size is about 1 millimeter, right? So you have a large spot. With the lasers, it's much smaller. It's our pixel size of our detector didn't allow us to compute back the source size, but we can make 50 micrometer big spots. So you have, for imaging applications, those lasers are not only very intense and brilliant in flux, but they also have a very small source size, so you can magnify. So this is an AWE tungsten target that was characterized at DART, the Dual Access Radio Hydrodynamic Test Facility at Los Alamos, for weapons testing. This is what you get there, and I hope I don't have to convince you that with Trident, with a single shot, now this is hard X-rays, you get equivalent or even superior picture quality. I think, yeah, so this shows how the cross-section, number of neutrons as a function of deuteron energy, grows exponentially. So if we get more energy into the deuterons with somewhat better lasers, we get more than linear gain in the neutrons produced. So that is all promising. Here is a landscape where laser energy and maximum proton energy, or half of that will be deuterium. With Trident, we were somewhere here. The new facilities in Europe, the extreme light infrastructure in Prague, they want to go in this field. And to give you an idea of the cost, the Prague Eli facility is about 300 million US dollar, 280 million euros for 4 of these high intensity lasers, including clean rooms, buildings, and all that kind of stuff. Compare the SNS was $2 billion, right? So a laser out here should produce LANSCE-like neutron fluxes, so we are at the cusp of this becoming a reality. And I think that's on this slide here. So at Livermore, they have this beam-in-a-box concept. There's a presumably technician or some person standing there, and there's this beam in a box, so I'm told this machine can run at 16 hertz. LANSCE runs at 20 hertz. It does 8 kilojoule of energy. At Trident, what I showed you was 80 joules, so this is a factor of 100 more. So the technology exists and it keeps advancing. And I'm not sure if you're familiar, across or down here towards Fremont, there's a company, LANSCE, that builds a synchrotron that fits easily in this room by replacing the wigglers that normally at a synchrotron make the synchrotron radiation with a laser. Right? That shrinks the ring. Normally a synchrotron, ALS or APS, they're half-mile diameter or something like that. They replace the wigglers with a laser, therefore the ring gets basically like this, right? Or like this here. And then you can build these compact sources that still are, of course, not as good as APS or ALS, but they bring you within reach. So this technology that once used to be large-scale user facility, now you can buy this thing for something like 11 million bucks and have a synchrotron in the basement here. That's a factor of 100 or so less than the APS, but if you don't do super fast experiments, you still get synchrotron radiation. So for neutrons, maybe someday that exists too. So now some little harder numbers. How far away are we from a laser lens? So we have 10 to the 10 neutrons per pulse achieved at Trident in 2016 with something like 70 joules. And as I said, they all forward, so they all get moderated. At LANSCE, when the proton current runs at 100 microamps and 20 hertz, we get about 3 times 10 to the each spallation process makes about 20 neutrons. So we have 6 times 10 to the 14 neutrons per pulse, but it's in this big tungsten piece. So if I take 1 order of magnitude off, and then more realistically I have to almost take 2 orders of magnitude off, I get 10 to the 13 moderated neutrons per pulse at LANSCE. So we're about 3 orders of magnitude away, but with target optimizations, with a stronger laser, we can regain that. The other thing is shielding, right? At LANSCE, I have to be 4.5 meters away from the source for shielding. With the laser, I don't make these super fast spallation neutrons that are hundreds of mega electron volts. So my shielding goes down. I can put my imaging sample a meter away from the source, or maybe 2 meters, right? And the 1 over L squares regains a lot of flux. So my point here is, I think we are at, let's skip this one. I think we are at a point where laser neutrons make sense. One part of the summary, right? So we develop methods at Los Alamos for characterization of nuclear fuels. We demonstrate them with whatever the nuclear energy program provides us with. And then we have the pleasure of developing also, joining or participating in the development of bringing that to the nuclear facilities. And with that, I leave you with my little summary. And mostly neutrons are fun. I hope you can join on that.
Do we have any questions from the audience?
Sorry for being in the middle of that.
So you talk a lot about kind of the hardware that goes with basically neutron imaging and all the possibilities that are available there, but the software side is also extremely important. Can you talk a little bit about those kind of developments, like how much is LANSCE investing in that versus this?
So software, we're mooching off the nuclear physics community that does these resonance profile analyses normally. So we use their codes that have all the bells and whistles for beam hardening, double scattering, and use it in a simplified form. Right now it's a bunch of scripts, right? So there's not much optimization, and to same as in diffraction, where you have also hundreds or thousands of diffraction data analysis and you want to analyze the difference curve. There are some efforts, but it's clearly a problem, right? To look whether 2 million fits have converged and what are the problems. And CT, we work with people at Purdue. Are you a CT person? So there are the whole field of having a multi-modal CT reconstruction that is new. The X-ray people now have dual energy, and they reconstruct at lower doses for the patients or the objects with those dual energies, but having a data set that does X-rays and 10 different neutron energies and reconstruct the same object. That is new physics that we barely start to explore, but if you have somebody who's interested in that, I'm more than happy to collaborate.
For time of flight, you need to have very, very fast shutters to...
It's 100 nanoseconds is good enough.
Oh, really?
The bin time. Because, I mean, the pulse is 50 milliseconds long, right? So for thermal neutrons, definitely no problem. And those fast neutrons, they come if you have 100 nanoseconds bin width, you're still good. But at 10 meters, that is not a limiting factor for what we want.
Right.
So it's not rocket science, or it's not like like super fast bin widths or clock times or something like that. So
because you're not using extremely high-speed neutrons.
Right. So we are happy. 100 electron volts is good, and then we have a 60-meter station where it further gets spread out, right? Mm-hmm. And then you have a factor of 7 or 8 more time to measure it, and it's not super. It's CAN digitizer boards for those ones, and then the MCP transient detector has about 100 nanosecond, I think, clock widths for bin widths.
Can you comment on how long it takes to record such a tomography? Very beautiful.
Yes, so...
If you think it's possible to do that in the next 10 years with lasers?
Well, I mean, at LANSCE it takes 3 days for a fuel, right? It depends on the cross sections. But the tungsten example, right, to get minute amounts of tungsten, tungsten has a 40,000 bar in cross section for that resonance, so it was a 3 to 5 day is a typical spin time for some 60 CT data sets. Was a laser driven, and that's measured at 10 meters, right? So and I don't need a lot of time of flight resolution for that. I just want the depths of the transmission signal. I don't need to really have 50 points on a resonance dip. So if I bring my sample to 2 meters, right? 1/2 is 4, 1/10 is 100. I don't expect humongously more time for a laser source that is 4 to 100 factor of 25 weaker, right? I mean, it's not out of reach. And at Idaho, when they have to ship a sample to us, right? I mean, that's a month of paperwork, 2 weeks of trucking. Takes me a week to unload and do the receiving paperwork. I mean, and then the cost, right? So it's. I think we should bundle our package here and get going.
So is that 3 to 5 days of 24/7
Yes.
at full rep rate?
Right. So it's not a quick technique, of course, if you can make it quicker. And the beauty of the lasers is, right, if I really want to spend $1 billion, I can buy me 20 lasers, they all feed the same moderator, and then I blow the ESS and the SNS and everybody out of the water, right? So I mean, that's the other exciting part of this. And I still don't make spallation neutrons. I still don't need that much shielding. So it's an exciting opportunity as a neutron person.
Okay, maybe one quick one.
What are the peak energies of these, of the laser neutrons?
The deuterons
The breakout
have,
neutrons.
yeah, the deuterons have a maximum energy of 20 mega electron volts, the way we made them. Half of that, or 20 mega electron volts is the top energy that you possibly, in the worst case, can out. Whereas in spallation, you make those 10% neutrons that come with 200-300 mega electron volts out, that drive your shielding, right? So probably want a little bit higher. But I mean, that's the case, it has to be calculated, right? I mean, how, for a given application, how does the flux go? Is it better to accelerate more deuterons, or is it better to have a factor of 10 less deuterons, but a factor of 50 more energy?
Yeah.
That's stuff that somebody has to figure out, or the community has to figure out.
Yeah, and bigger shielding problems.
Right, I mean, what's the compromise with shielding, right? I mean, if I don't want to go into the 4 or 5 meters, or the ESS, the closest shielding, the bunker is at 20 meters, at the SNS in Oak Ridge it's 15 meters, right? My Hippo is at 9 meters. If you compute that 1 over L squared, they don't get much. They have a 10 times more intense source, but they lose a lot off the bat right there. If I do that for the lasers, I don't want to lose that benefit of needing less shielding, unless I really, really have to.
Okay, well, thank you so much, Sven. It's a lecture-free day, so this does not count as a class. It's purely volunteer to get something about laser-driven neutron sources.